to wind engineering because we need to understand not only earthquakes but also wind load, which is important encoding for all slender structure. This is the structure. It's a tall stack in Rayong, not very far from here, about 2 meters. And we actually helped the designer to design the structure, and we found that the structure is quite vulnerable to wind load. Wind can produce oscillation due to the vortex. The vortex wave of the wind can create a periodic fluctuation in the pressure of the wind pressure around the stack. And from our analysis, at some low wind speed, it can produce the wind oscillation in this structure in the first mode at low frequency. And when the wind speed goes to some higher level, it will induce oscillation in second mode. So in this project, we then propose to the plan to adopt this measure called roughness. Okay, this is a kind of steel ring hang on top of the stack, connected by wire rope and this hot damper. Okay, and we put 2 of them on the top of the stack. One of them designed for the first mode with a wing mass of 5,000 kilograms. Another one is 2,000 kilograms designed for the second mode. So these are two dampers suppress 2 vibration modes at the same time. To show our team from AIT and our research partner and also from AIT Consulting, we work together. One day we can tune these 2 dampers. Just finish all the work in 1 day and then go home. So that's done quickly. And at the moment we are now designing a larger damper for one of our buildings in Bangkok. And the damper doesn't look like this. It's clearly water tank. It's called sloshing damper. This is our wind tunnel lab that we developed together with Thailand University. It allows us to investigate the wind load and wind effects to tall and slender structure. This is a section of the bridge model in Vietnam called roughness. This is another type of structure that we test in our wind tunnel. It's a billboard structure. The model is small, but it actually represents structure like this, which is about 50 meters tall, very wide structure and very vulnerable to wind load. And many of them collapse during thunderstorm. Okay, this is a 50-meter tall billboards. This is another case. Some years there are more than 10 billboards collapse in Bangkok area. So this is a very serious problem. And the wind that caused the damage to this billboard are basically thunderstorm. It's a small scale wind, but it could produce very high wind velocity near the ground. If we compare to the typical velocity profile that you use in wind resistant design standard, the thunderstorm wind profile is quite different. So it can produce very high wind load close to the ground. And this is our model. We have a model put on the dynamic force sensor that allows to measure not only the drag force but also the twisting moment and overturn moment and many other force components. So if you adopt the wind code, simplified wind standard, it may give you this kind of uniform wind pressure where the net force is acting at the center of the billboard. But when you conduct the wind tunnel test, you will see that in most of the cases, wind pressure is not uniform. And it may create not only the drag but also twisting moment at the same time. And this may lead to critical effect in some critical members So we test not only one, but also many types of configuration to understand it, and we put all the knowledge into our new standard. This is another interesting project called image in standing configuration. The structure is quite, the shape is quite complicated, and you cannot find the window guidance from the design code. So we have to test it in the wind tunnel. This shows how the wind varies with the different wind attack angle, but I don't think I have time to go into details. It shows the force, we call drag force and slide force, for different direction of the wind. With this information combined with our knowledge in structural engineering, where we compute the first vibration mode, second vibration mode, and torsional mode, we can then calculate the response. Okay, this is the top detection. And we can calculate the stress, the force in the internal members. We can compare with this, capacity, so we can create what's called capacity picture. That allows to quickly identify members that are overloaded and maybe in danger. So we can actually check the performance of real structure by this approach. You can test also for buildings. This is a 70-story privacy residential building in Manila, Philippines. The building, there are many nearby buildings, and nearby buildings can modify the wind flow. So we can put all these effects into our wind tunnel. And where the principal building is located at the center. And we can then check the load applied to this building. Okay? This is a different model for the same building, but this model is used for measuring the pressure, wind pressure around the structure. This is for us to identify the load to decide the cladding of the building. Okay. I think that's complete. This will be the last set of slides. So this the project here is about the dome structure. And this is the project we just finished about last month. It's the dome system. It looks like this. And to design this dome structure, which is a very light, non-span dome, you need to know the wind pressure information. Okay? This is how it looks like. We measure pressure at different locations on the surface of the dome. We measure all this pressure, all of them at the same time. And this is the wind direction coming from this side. And when the color is orange or higher than yellow, it means the pressure is pushing to it. High pressure, higher than atmospheric pressure. When the color is green or blue, it means the pressure is lower than atmospheric pressure in suction. So on the top of the dome, it creates a suction effect. On the front of the front side of the dome is create a pressure. This complex dynamic loading is acting on our dome structure. And the wind tunnel test allow us to see this information. And we supply this to our AIT consulting engineering team. Okay? And they use it to analyze the dynamic response of the dome. How they do it is their problem, but we just start the data. Okay? So this gives you some idea that this modern techniques allow us to get more